Today we're going to start looking at Unit 4 of this course, Geometric Vectors. It'll be the last unit we cover before we do the midterm exam in April. So if you're falling a little bit behind or you're right on track, that'd be good to know at this point. The 4 units we cover for the exam will be geometry and measurement, trigonometry, periodic functions, and then this one here, vectors. And we put them together because it mostly involve shapes and drawing things and trigonometry, to be honest. So today we're going to start looking at geometric vectors. A lot of definitions today, ideas today, not a whole lot of math per se. You are going to be drawing some pictures over the next couple of days when you're doing these lessons, so having a ruler with some measurements on it would be handy to have nearby. In this first lesson here, our big idea today is to be able to tell apart scalars from vectors. And a scalar is anything that has a value that can be expressed by a single number. We call that single number the magnitude. The size of something. Okay, so for example, time could be 3 hours. Well, that's a number, right? It's a size. Temperature, -5 degrees Celsius. Temperature, again, just a single number. Your volume, 426 meters squared. Yeah, just a number. Yes, they have units, but they have only a single value to them. As opposed to a vector, which is something that can be expressed in terms of a magnitude and a direction. And so for example, velocity, you're driving 60 kilometers an hour east. If I were to draw that out, I could say I'm going this way. Okay, so I'm going in a certain direction at a certain speed. Gravity, -9.8 meters per second downwards. It's going this way. I can draw an arrow, if you will, that signifies what's going on here. Okay. There are a couple of these that are very close sounding kinds of things. So this little table here, scalars and vectors, try to help you out a little bit. Distance is a scalar measurement. I've walked 5 kilometers. As opposed to displacement, I walked 5 kilometers east. The only difference is I have a direction there, right? Speed, my car is going 60 kilometers an hour. And my velocity, though, is 60 kilometers an hour west. I have a direction there also. And one of the trickier ones, mass. You might say you weigh 65 kilograms, but that's actually your mass. Your weight is what's holding you down on the earth, so it's 65 kilograms downwards. So be careful a little bit when you're talking about vectors and scalars. Is it just a number or a number with a direction? Example here, we'll try some of these. We'll see if we can figure out which ones are which. Okay. So 24 students in math class. Oh, that's a number, right? It's just a scalar. No directions there. The airplane flew 515 kilometers. So I got a number at a bearing of, a direction of, tells me it's a vector. Okay. A 30 kilometer an hour north wind, size, direction, vector. 5 people living in the house just north of yours. Well, the 5 people aren't walking to the house north of yours. They are in there, right? They're not moving from one spot to another. This is just a number, just a scalar. Yeah, there's a little trick there. I tried to put a direction in there, but it didn't really mean anything. Jeff drives at 100 kilometers an hour for 40 minutes. It doesn't tell us where he's driving, so we have no direction. It's a scalar. Jess jogged 6 blocks west. Okay, we have a size and a direction, vector. And the boat was headed north 42 degrees west across the lake. Now, this is a bit of a tricky one. This is actually a vector, and we have our direction. And across the lake, well, however big the lake is, it's going to have a size attached to it, right? Something like that. So even though it doesn't have the number in there, it actually is a vector. The last one here, the tires were worn out after 120,000 kilometers of driving to and from work. Okay. Well, the to and from work is throwing you a little trick there again. It really is just a scalar. We didn't drive to and from and to and from and to and from and do all those things over and over and over again. We took little breaks in between those two things, right? So that's just a scalar thing. To talk about vectors, a vector itself is actually the line segment. I sort of drew that out on the first page there, right? We just said 60 kilometers an hour east. Well, my vector is going to have a line that represents it. That line kind of needs to have a scale attached to it. So maybe it's something like, oh, this is 3 centimeters. And we know each centimeter represents 10 kilometers. Okay, so I have a scale, I have a size, a magnitude, if you will. And it also have a direction. Whichever way the arrowhead points is the direction of this vector. So this vector I've drawn is one vector. This would be a totally different vector. It's pointing in a different direction. Hey, maybe it's also a different size. We didn't really measure that one. A little bit of terminology for you, or notation. Any vector that starts and ends at 2 different points can be labeled with those points. So if I go from point A to point B, I write it as A to B. And A is your tail, and B is the head, as the picture shows you here. And it's hard to see it, I guess, a little bit, but the symbol above the AB is sort of like a half arrowhead, and that signifies that you have a vector. So whenever we label vectors, we can put this little arrowhead over top of them. Okay. If we didn't have starting and end points, we could use a lowercase letter. For example, V, we could call that a vector. We'd use that in a situation where like these ones up here in the top, we'd call these V's because we don't have any labels, any tails or heads, any A's or B's. Okay. And one more little idea, the magnitude, the size of your vector. And we use these absolute signs to label the vector. And what absolute signs do is they take the sign off of a value. So -5, the absolute of that is 5. It's 5 units from 0. The sign doesn't matter. The absolute of 6 is 6. The sign doesn't matter. Everything becomes a positive. And the reason we use that is when we're talking about vectors, the magnitude of a vector must be a positive. Okay. Some more terminology. Equal vectors. Remember, vectors are imaginary lines in space. So we can move these vectors around. We could draw one over here. We could draw another one over here. And we might want to ask ourselves, are these the same vectors? Well, if they are the same vectors, if I were to move them closer to each other, okay, these two vectors would have to have the exact same size in the exact same direction, which you notice these two do, right? If that is true, they're considered equal vectors. Same magnitude, same direction. We say that A equals B. And the example I gave you did that. Opposite vectors, on the other hand, have the same size, so same magnitude, but they go in opposite directions. So looking at these A and B down here, okay, the arrows are the same size, but they point in opposite directions. And to show that, we say that A equals the negative of B. And the negative sign tells me I'm going the opposite direction. And that's where that comes from. Same size, but opposite direction. Okay. Taking that into account, let's go to an example here. I got a parallelogram. Parallelogram, if you remember, means these two things are parallel, so they're pointing in the same direction. And these two things are parallel, so they're pointing in the same direction. Kind of handy when you're talking about vectors, these imaginary lines in space. So I want to list pairs of equal vectors. So I could say AB, that's a vector that goes from A to B, is exactly the same as D to C. Because D to C is the same length in the same direction. And the order makes a difference here, right? My tails have to be in the same spots, my heads have to be in the same spots. I could say something like BC equals AD. That would work. From here to here is the same as here to here. Those are the same directions. If I want to, I could list a couple more. I could say, let's do this backwards. D to A is the same as C to B. Those would be equal vectors, right? So the exact same length and the exact same directions. Okay, that's part A. Part B, that's pairs of opposite vectors. So I want to start with AB. AB we said was this one. What would be opposite to that? Same size, opposite direction. That would be this one, right? Same size but opposite direction. So we'd say AB and, order matters here, CD. And the heads and tails are in opposite spots. I could say BC. Well, BC's opposite B. D, A. And again, I could repeat some of these, but that's the idea. All right, part C. Is AB equal to negative CD? Oh, what's that asking? Well, AB and negative CD. That's, by putting this negative sign here, it's asking, are AB and CD opposite vectors? So let's take a look. AB goes here, and CD goes here. Are those opposites? Sure they are. So we'd say yes. AB does indeed equal the negative of CD. And the negative CD, another way you can write that down is the negative sign means it goes the opposite direction. That's the same thing as saying DC. So does AB equal DC? It sure does. Okay, and there's a little bit of terminology for you. As I said earlier, we're going to draw lots of diagrams. We're going to draw lots of scale diagrams. This first one here, I just want to work with the scale diagrams to get used to labeling vectors. Okay, we often use bearings in here too. That's why we did trigonometry before we started doing vectors. Okay, I want to describe each vector and its opposite vector in words. So what I need to do is take my handy dandy ruler. You guys can use a ruler on your own. And I'm going to measure this thing. How long is it? According to mine, this is 4.8 centimeters. So I would say V is 4.8 centimeters. That's my size. I need to give a bearing here now. So if I go to the east first, then I can go 22 degrees towards the north. And from vectors, that would describe this angle, right? Now its opposite vector looks exactly the same, but it goes in the opposite direction. So if I were to draw that out, okay, it would be going this way, right? Okay, so what would the difference here be? Well, this is still 22. My size, we'll call this, let's call this one U, just so we can tell them apart. So U is still 4.8 centimeters, right? The magnitude doesn't change, just the direction does. So instead of going east 22 north, I would be going west 22 to the south, the complete opposite direction. Okay, if you guys want to try the next one, use your rulers. And how long is that? That's about 4.6, it looks like. So I'd say 4.6 V is 4.6 centimeters at, this time I'm starting at south, and then I'm going to go towards the west, with my ruler here a little bit, 53, south, 53, west. If I were to draw the opposite in there, it would look exactly the same. 4.6 long, but it'll go the opposite direction, right? So if we call that one U, as I said, U is 4.6 centimeters at, and this time we're going to go to the north first, and then go 53 towards the east, the exact opposite direction. Same size, opposite direction. Okay. Got two little examples left here. Draw an appropriate scale diagram for a vector of 50 kilometers on a bearing of 120. So the first thing I need to do is I got to decide on a scale. So I'm going to say 1 centimeter is 10 kilometers an hour. Then when I take my compass, a bearing of 120, so I take my ruler, where's 120? There's 0 and 90. So 120 will be down here somewhere. And move that up there. Say about 30 degrees. And I need to go 50 kilometers an hour. So according to mine, that would be 5 centimeters. Okay, my tail's at the origin, my head's there, and I know this is 120 degrees. And there's a scale diagram, which you're going to have to do a few times today. Okay, last one. We've got Rhonda. She lives 5 kilometers from Murillo in a southwest direction. So Rhonda, southwest, 5 kilometers. This is Rhonda. Okay, and we have Travis. He lives 5 kilometers southwest of Pass Lake. This is Travis, 5 kilometers southwest. And we want to know, are these two vector quantities equal? Well, if I drew them accurately, they have to be, right? They're the same length, so same magnitude, and the same direction. So are they? Yes. Okay, and that takes us to the end of geometric vectors.